Hi folks, welcome to this video here. Unfortunately I've got nobbled for a meeting today during period 5 when I would normally be seeing you, so I've had to put the work that we're going to do today onto this video here. So what we're going to be doing is to extend the work that we've been looking at recently about using the definite integral to find areas under a curve. So in a moment, I'm just going to briefly summarize the key points of where we're up to so far, and then we're going to have a look at a couple of situations, one of which we touched on previously, which is where we're trying to find an area where part of the area we're trying to find is above the x-axis and part below, and then we'll have a look at where we've got an area basically sandwiched between two curves and how we can go about trying to find the area between two curves. Just wanted to point out before we do that this bit of material here on OneNote. It's here under in the content library under integration area under a curve. There is I did mention the other day that if you're looking for a mathematical proof, you're going to have to wait till university to prove the this idea that the area under a curve is equal to the definite integral. There is a proof here on this website, this link to this website here, which a number of you should be able to follow, and it's quite a good proof, and you could have a look at that if you're interested in trying to get a bit more of a proof about this work here. Okay, so also I do mention here a video about the work that we've covered recently. I haven't got the link here right at the moment, but I will put that link in a little bit later, and yeah, you could have a look. This is the work that we've already done on areas under the curve. If you're interested in seeing some further work about that or some further explanation, that'll be there a little bit later. Okay, so what we're going to do then, if we're just going to jump from this view here to another view, just going to get that up here. Okay, so what we're going to basically do, just summarize the key points so far. So what we're looking at is a situation where we're asked to find, say, an area like this one here that I've shaded. It's for some function that's produced this line here. Excuse me, and we're trying to find the area bounded by the curve, the x-axis, and these two lines here. Okay, and what we've seen is that the area, this shaded area here, is equal to this definite integral. And just to take this one stage further, if this integral, the integral of this function here, if that is equal to, say, capital Fx plus c, then the area would equal that antiderivative, that integral with b substituted into it, minus what we get when we substitute a into it. And we've already discussed why we don't need that plus c, because we had plus c and a plus c here, those two things would simply cancel every time. So this area is equal to the calculation of this definite integral. Okay, I'm just going to pause the video and yeah, we'll have a look at the next part just in a moment. Okay, just back here now, folks. So we're going to have a look at an example where we've got this function, the one shown by this orange line here, and what we're trying to do is to find the area that I'll just highlight here. So this area which is there, and this area which is here. We want to find the sum of both of those areas. Okay, so how would we do that? We've got part of the area above the x-axis and part below. Now what you might recall was that the area above the x-axis, when you calculate the definite integral, say between this point here and this point here, will be positive, but the definite integral for this function, if we calculate it between here and this point here, okay, will be negative. So what we're going to need to do is we're going to need to split this the area that we're after into two parts. We'll find this area here, let's call that area A, and we'll find this area B here by taking the absolute value of the definite integral. Okay, so when you've got the part of the area above the x-axis and part below, that's going to be your strategy. Split the question into two parts. You cannot integrate between, let's call this point here A, B, and C. If you calculated the definite integral between C and A of this function, and you calculated that and got a result after some working, okay, whatever numeric value you get is actually going to be the difference between these two areas here, and you actually end up with a negative answer, because in this case this area here is much larger than this one, so this definite integral will be more negative than this would be positive. So whatever you get here will be the incorrect answer. Alright, so let's push on and see how we would actually calculate this then. Okay, I've actually indicated some points here that are going to be important, these A, B, and C values. Well, this actually does factorize quite nicely. If you factorize this, you can take a common factor of x out, x squared minus x minus 2, which then factorizes one stage further to x minus 2 and x plus 1. And if you think about the roots, i.e. the x-intercepts, that would be at 0, 2, and negative 1. And yes, I realise the scale of this isn't quite right. So that'll help us to get the limits, these values here, on our definite integral. Okay, so let's calculate the area then in two parts. Come on, pen, move. Okay, the integral between 0 and negative 1 for this function. Let's call this area A, and let's do the bit of work here. So we're integrating, so we add 1 to the power, divide by the new power, and we just do that for each part here, because this is simply a power function, in this case a polynomial. And we can calculate that between 0 and negative 1. Okay, this will cancel down to just x squared, and if you put 0 here, here, and here, that becomes 0 minus what we get when we put negative 1 in. So negative 1 to the power of 4 is 1. Negative 1 in here becomes negative 1, so minus negative 1/3 becomes plus 1/3. And minus, when you put negative 1 in here squared, that becomes minus 1. Okay, so we're going to get a quarter plus a third. That actually works out to be 7/12. So it's going to be 0 minus 7/12. Take away 1, which is 12/12. So if you do the maths, this is going to be negative 5/12. The negative of that, positive 5/12. So that is this area here, 5/12. Okay, then we need to find this area B. Okay, this one here. So I'm going to fit that hopefully over here. So we're going to integrate between 2 and 0, same function. But the area is going to be equal to the absolute value of this. Okay, so think we'll put the absolute value symbols just at the end. I think that'll be fair enough to do that. Now we've already integrated, we've done that work here, so let's go straight to that. Let's put 2 in, so it's going to be 16 over 4, which will be 4. That'll be 2 cubed, which is 8 over 3, so minus 8 thirds, minus 2 squared, which is a minus 4. Okay, and if we substitute 0 in, we've seen before that that's already 0. Okay, so this comes out to 4 take away 4, if I'm not mistaken, just double checking that. 2 to the power of 4, 16. 16 divided by 4 is 4. 2 squared there is 4, yep. So they're going to cancel. So the area will be equal to the absolute value of this negative, which is 8 thirds. So the final answer, the area required, would be positive 8 thirds plus the 5 twelfths. Okay, which is going to be, let's do a bit of fraction work, times those top and bottom by 4, 32 twelfths plus 5 twelfths, going to give 37 twelfths. And let's just put units squared for the area. Okay, so that's an example where we've got area above and below the x-axis. Okay, the last example we're going to look at, last situation, is where we've got the area sandwiched between two curves. Okay, I'm just going to pause the video and get back to that in a second. Okay, well, we're back here, folks. Okay, so in this situation, as you can see, we've got a couple of functions here, and there's an area that is sandwiched between the two curves. And let's say you're asked to find that area. Okay, so what we're going to have a look at is, well, this idea. If we get the area underneath this curve f between the two limits, and let's actually put those limits in. Let's go to that color. So this point where the two functions meet, that will be one of our limits, and the other limit, the limit of the integral we're going to use, call that b. Now if you get the area underneath function f between a and b, it'll be equal to this area I'm shading in blue. Now as you can see, that area shaded in blue includes the area in orange that we're after. And if we get the area underneath function g, let me choose a different color for that, then this will be this area in red. So if we take that area in blue, which is underneath function f, and get the area which is underneath function g between a and b, which is the area in red, well, that would leave, if you take the difference between those, take the blue area, subtract the red area, that will equal the area which is in orange. So just to emphasize that again, so area in blue minus the area in red would equal the area in orange. Okay, so what does that mean mathematically? Well, we need to have a look at an example. Okay, so what we're going to have a look at here is question 177 on page 206. Now this is an application then of this idea of getting the area between two curves, but I've deliberately taken one which has got some challenges to it. Okay, so if you're looking at the question on page 206, you'll see the area that's in orange in your workbook is basically the area sandwiched between this green part of the curve, this orangey part here, and this brown part here. So it's I'm not going to shade it in, but I'll just demonstrate on the screen. So it's all of this area between those colored sections. Now I've deliberately labeled them A, B, and C. So we want to get the area called A, this part here. We want to get area C, but we don't want to include this area B here. Okay, so what I've written up the top here is what we would get if we calculated the following definite integrals. Okay, if we took the definite integral between 1 and 4 for function f. So what's function f? This is this top function here, the part in green and the orange. What we would get is, if you calculate the definite integral, you'd go from 1 to 4, and so effectively for the area, that would include this area, which is area A here, which is what we want, but we would subtract this area B. That's what happens when you calculate the definite integral. Okay, where part of the area is above the x-axis and part is below. So it'd be area A minus area B. Then if we calculated the definite integral for function g, and so what is function g? I'm calling this function g. Okay, so this is this brown part here. Okay, if we calculate the definite integral between 4 and 1 and 4 for that function g, okay, because the area is below the x-axis, it would be the negative of area C plus area B. So we get the total area here, but it'll be negative. So it's a negative of the sum of those two things. Okay, and so if we then said, okay, well, how am I going to get area A and area C, these two ones, but not that area B? Well, let's consider what happens if you actually took the definite integral for function f and subtracted the definite integral between 4 and 1 for function g. Okay, I did all of that. Let me just fix that up a little bit. Okay, so we should have the dx's in there. Okay, what that would be area A minus area B. That's this result up here. Now we're minusing this negative thing here. So minus the negative area C plus area B. Okay, let's see what that turns out to be. That'll be area A minus area B. And this part in here, if we expand the inner part here, be minus area C minus area B, if you put the negative into this inner bracket here. And then let's tidy this up, and I'm just going to go down here where I've got a bit more room. So this will equal area A minus, that should have been a B, minus area B. Now if we expand the negative into here, be so plus area C, the negative of a negative being positive, and that'll be plus area B. Okay, can we simplify this a bit? Well, yes we can. Notice we've got negative area B and positive area B. Well, they're going to cancel, and what we're going to be left with is area A plus area C. So what we've effectively got then is the area that we're after, A plus C without B. So how did that happen again? Well, we simply took the integral between the limits 1 and 4, the top function, one at the top of the graph, of the two graphs, minus the integral between 1 and 4 of the bottom part. Now, what we've done here for this particular example will always work. So when you have two graphs, an area sandwiched between two functions, okay, the area that you're after will always be the integral between the two limits of the top function minus the definite integral between the same two limits of the bottom function. Okay, so I'm just going to summarize that on a different so I'm just back here on this graph that we were using earlier, and so what we would have if we generalize this is that the area that we're after will always be, so the area required if you have the area sandwiched between two curves will always be the integral between B and A of the top function, and you'd need probably a graph to see which is on top, minus the integral between the same two limits of function g. Now you can actually combine these two. This is algebraically correct. You could actually then calculate simply the integral between the limits a, b of function f minus function g. Sometimes that's simpler to do algebraically. Okay, so yeah, what we'll do is we'll finish off that previous example with a little bit of algebra just to get the numeric value for that. Okay, so let's get back and finish this one off here. So we looked at this before. So the area we're after is the one shaded in orange in your book. So the top function, this one here, okay, is actually function, I think, g in your book, actually. So my apologies about sort of mixing the f's and the g's up there a little bit, but it is the cubic function is the top one. So we're going to take that top function minus the same integral between 4 and 1 of the bottom function, which is the quadratic one, x squared minus 5x plus 4. Now, rather than calculating these things separately, as I mentioned just a moment ago, this is equivalent and equal to that minus this. So we can take that cubic and subtract the quadratic. Okay, so we've got x cubed, there's no other x cubed term, minus 8x squared, and that'll be minus x squared, so minus 9x squared, 19x, and it's going to become plus 5x, so it'll become plus 24x, minus 12 minus 4 will be minus 16. Okay, so this area should be equal then to this definite integral. Okay, so if we integrate, these are all parts of a polynomial, so we just integrate by using the basic power rule. It's a definite integral, so we don't need the plus c. Okay, I'm just going to pause the video and calculate what this is equal to. Okay, so having finished off the calculation, what we find actually when you substitute 4 into this, and of course you could simplify parts of this, that would become 3x cubed and 12x squared. This actually becomes 0, and this becomes negative 27 over 4, but we're subtracting, so it becomes plus 27 over 4, which is 6.75 units squared. Okay, alright, so in terms of the work that you're going to need to do, basically you need to work through the questions starting on page 202 all the way through to the questions on page 208. Okay, so that's quite a few there to try and work your way through. So page 202 to 208. Alright, we'll see you in class tomorrow.